My pleasure to introduce our speaker, one of our very own, Yuan Yao. Yuan is an assistant professor of industrial ecology and sustainable systems here at the Yale School of the Environment. She has been with us since 2020, and she received her PhD from Northwestern in 2016. I think if you look over Yuan's work or you even talk with her, you realize that she is motivated by solutions to our environmental problems, and that really drives a lot of her work. And she's extraordinarily interdisciplinary, and I think brings out some of the best of what we strive for in this school. She combines engineering with pretty much any other technique that you need in order to address these concerns. She is incredibly productive and publishes work in high impact places. And it is a pleasure to hear about her work again today through her research. So thanks, Yuan.
Thank you for introduction.
All right.
Thank you for clapping. Give me time to leave the timer. All right, hello everyone. Today I will talk about life cycle systems modeling for sustainable pathways to a circular bioeconomy. I'm sure many of you have heard of the concept of a bioeconomy, which encourages the use of biomass to replace fossil fuels for producing chemicals, fuels, and all kinds of products used in our society. When I say biomass, it's actually a very broad category that includes different kinds of natural resources. The figure I put here actually shows you some examples, like those plant materials from forest and agricultural sectors, or residue and waste materials generated by us, human beings, or animals, or from different industrial sectors. In the recent years, we have another concept called circular bioeconomy being developed. So this concept encourages the use of not only dedicated biomass like energy crops, but also waste and byproduct biomass by turning them back to ecosystems or converting them to some valuable product that we can use in our society. Forest plays an essential role in this concept of circular bioeconomy because it is one of the most abundant biomass resources available on the earth, and it has already been widely used by industries to produce different products. I put the photos here to show you some examples. Traditional wood products like furnitures and construction materials, pulp and paper product. We also have a lot of waste woody biomass already be turned into bioenergy and biofuels. We have many ongoing research to develop new bio-based products from wood. The photo I put here is a textile material for our clothes made from pulp. Those products have very different functionalities, but they all have very similar life cycles. They start from biomass cultivation, like tree plantation. We do harvesting, we collect those biomass, ship them to manufacturing facilities who do conversion to turn them into different products. Those products are used in our society, and once they reach the end of their lifetime, they may be landfilled, recycled, or burned for energy purpose, depending on how people want to treat them at their end of life. Biomass is a renewable resource, but it does not mean that utilizing biomass is completely environmental burden-free, because many activities I show you here along their life cycle may generate impact on the environment. So if we want to develop and promote a sustainable circular bioeconomy I put on the top, we have to answer several very big questions. First one is, what are the potential environmental impact if we use different biomass in different ways? What are the economic implications? Are they economically feasible? What are the societal benefits or potential risks? Are there any trade-offs among different aspects of sustainability? To answer those big questions, some tools available in our industry ecology field can be really helpful, such as life cycle assessment, a standardized tool to evaluate the environmental impact across the product life cycle, material flow analysis that can help us to understand and track the energy and the material flows across industrial systems or between the environment and industries. We also have economic input-output analysis that has the environmentally extended applications to allow us to quantify the environmental impact of one product or one service across economy-wide supply chains. Those tools are all very powerful, but they have limited capabilities in answering those big questions I showed you in the previous slide because of these very unique multi-scale challenges people face when they try to evaluate and assess different biomass utilization pathways. When I say multi-scale, this scale can mean different things. It can mean spatial scale, different locations, different regions. It can also mean temporal scale, different time. So when we collect the biomass from different locations at different time, we may end up getting biomass with very large variations in their quantity and also quality, like biomass composition. Ecosystems that supply biomass are often dynamic. Using forests as an example, if we look at those trees grow at different places with different rotation cycles being harvested at different times, they may look very different. Similar to ecosystems, those industrial systems also have this multi-scale effect. If we look at the environmental impact of just one manufacturing facilities versus we look at the environmental impact across the supply chain or even across economy-wide adoption and application of one bio-based product, those environmental impact would be very different. Traditional industry ecology method like life cycle assessment are static method. They have limited capability in modeling those dynamic systems. We also don't have enough knowledge to understand those multi-scale effect of complicated biomass systems. So my research focused on addressing those multi-scale challenges from both methodological and also knowledge perspective. And I draw those approaches from three major field or say disciplines: industry ecology, sustainable engineering, and also data analytics and systems modeling. So in the rest of my presentation, I know this looks very abstract, so I will show you several interesting examples to demonstrate how we can use those multi-scale system analysis to advance our fundamental understandings of those complicated dynamic biomass systems and also support decision-making. The first example is about the biochar, one of my favorite bio-based products. Biochar can be made from different kind of biomass, which is a carbon-rich material, and biochar has very broad applications. You can apply biochar to agricultural land as soil management. You can burn it as an energy source. You can also upgrade biochar to activated carbon, which is commonly used for water treatment. So if you have a water filter at your home or in your office, check inside. Highly likely you will find this activated carbon material there. The challenge here is activated carbon is upgraded from biochar that can be made from all kinds of different biomass. I put some examples here, like pine, eucalyptus, maple, so many others. When we use different kind of biomass, they have a different biomass composition, like moisture content, carbon content, ash content. Different composition would give us different mass and energy balances of the manufacturing activities, which will ultimately affect the environmental impact of this material. So if we want to understand the environmental footprint of this material made from different kind of biomass, we have to do life cycle assessment for each of them, which is extremely challenging because in current literature or existing database, there's no data and knowledge can tell us how the mass and energy balances of this manufacturing process would be different if we use different kind of biomass. So in order to fill this critical knowledge and data gap, we develop an integrated modeling framework that combines artificial neural network, a machine learning approach, with traditional chemical process simulations and chemistry kinetic models. I will not go into the technical details of this one, but I want to highlight the input and output. What we can get out from this model is that we can get out those important data we need to do life cycle assessment, such as energy consumption, the carbon emissions, the composition of our solid and gas output. Solid output really matter in terms of property and quality of final materials produced, while gas output may be emitted as environmental emissions. And the input for this modeling framework are all those data people can measure in their lab, such as composition of your biomass, the operational condition like temperature and residence time of your pyrolysis and activation, two major unit processes we need to convert the biomass to activated carbon. So we use this modeling framework to estimate how much energy we need to consume in order to produce 1 kilogram of this material from 7 typical woody biomass. 4 of them are hardwood, 3 of them are softwood. Different colors here is to show you different energy consumption breakdown by different unit processes. You may notice that we have a negative value here. This is because we consider burning gas products to recover energy. We also estimated greenhouse gas emissions and track their carbon sources. Like in this figure, purple color shows you the GHG emissions coming from fossil sources, and green and yellow color shows you the methane and CO2 emissions come from biogenic sources. And we all know carbon sources really matter when we do carbon accounting. So those are the results for 7 typical woody biomass. In total, we did estimations for more than 200 woody biomass samples. So this table is just to give you a statistic summary of all the energy and carbon emission indicators we generated. The number here shows you the average value, and the number within the pyrolysis shows you the ranges. You may notice that some ranges looks pretty broad, right? So this indicates the large impact of biomass composition on the energy consumption and carbon emissions of this material. In the paper we published, we transparently disclosed all the data and results we estimated. So for researchers who use this material in their system, like say for water treatment or for soil management, they want to do a life cycle assessment, but they do not have data for the upstream production of this material. They could just come to our paper, find the data they need, as long as they know what kind of woody biomass is used to produce it. We can also use this model to understand what are the impact of biomass characteristics. So those are the 2 figures that shows you the energy consumption versus the hydrogen content and the hydrogen carbon ratio in the biomass. Both of them tell us that if we use biomass with low hydrogen content or lower hydrogen carbon ratio, it requires less energy. I think this is a very useful information for people in industry or engineers who may want to do some biomass screening when they have a long biomass candidate available and before they start to do expensive and time-consuming experiment and life cycle assessment. So I want to use the example to show you how we can use a combined mechanistic engineering simulations and data-driven approaches to obtain micro-level understanding of individual biomass conversion technology, especially to understand the impact of biomass species and biomass composition, because this is a foundational knowledge for us to further develop regionalized process-based life cycle assessment to understand what would be the environmental implications if we scale up any of those solutions and implement them at different locations where we would get a different kind of biomass. We can further scale up this knowledge to be combined with geospatial analysis so we can understand what are large-scale environmental implications for those scalable solutions. So now I want to demonstrate this life cycle modeling framework through a case study we just published last year, and we study those waste of materials coming from urban forest, which we all know is a very important component in our urban systems. They provide a lot of benefit. They modify our microclimate, they can mitigate the pollution and noise. And in urban area, most of the time, we can see 3 types of urban tree waste. The first one is those big chunk of trees. They can be removed for many reasons, right? Like urban planning, different activities, people have different expectations of what their front yard or backyard should be looked at. The second type is those residues like limbs or branches people cut down when they do trimming. The third one are those leaf waste. I'm sure many of you have seen those on your backyard and maybe thinking about how to get rid of them. There are several common ways to deal with those urban tree waste. First one is we just send them to the landfill. Sometimes people don't want to pay for a fee to haul them away, so people just leave them on site. Either way, those biomass will go through decomposition and generate some GHG emissions. For those removed trees, people may chop them into a fuel wood and burn them for energy purpose, such as heating up their houses. This is a photo I took last year when I hired a contractor to remove a tree in our front yard. It was really fun to watch how people do this in real life when we were doing a research project on utilizing urban tree waste. And my contractor, they actually didn't chop them into fuel wood. Instead, they put a giant grinder after this truck showing the photo, and that grinder actually chopped those wood into even smaller pieces, which we call them a mulch. So I put a photo here down the bottom to show you what mulch looks like. But if some of you want to see more of them in real life, I suggest you check that little gardening area in front of Kroon. When you walk out after this seminar, there are plenty of mulch there. They can do a very good job in suppressing weed and also improving moisture retention. So that's why you see them a lot in those city gardens. For those leaf waste, we can't turn them into mulch. They also don't do well if we combust them, but they are rich in nutrients. So sometimes people also do composting for those leaf waste. The photo I put here on the top is a very common wild composter. You can find it in many shops like Home Depot. In addition to those pathways, there are some emerging pathways in the recent year that people also want to try to allow a full utilization of a different kind of urban tree waste. For leaf waste, we still want to do composting, but for those removed trees, if they have a big diameter, they can be sold as merchandisable logs to lumber mills nearby, who can turn them into different kind of durable wood products in buildings and usually have a long lifetime before they get sent to landfill again. And then for those forest residues and smaller diameter trees, we can collect them, convert them to biochar, and apply biochar to gardens or agricultural land for soil amendment. If we want to understand environmental implications of implementing those solutions in our world, we also need to understand what other materials in the market would be affected, such as those reduced usage of fertilizers or those materials and products that could be replaced by biochar. So now we applied the life cycle modeling framework I showed you previously. And the first step for us is always to develop mechanistic engineering simulation models for each manufacturing steps and utilization pathway. So the figure I show you here is a simplified process flow chart to show you what are those activities and unit processes we include when we model biochar production. And after biochar is produced, we also include transportation and field application. The purpose of developing this kind of model is really to understand if we collect urban tree waste from different locations that have variations in their composition, like those properties, how those variations would affect the energy and the material flows and environmental emissions, because those are critical data for us to do life cycle assessment. And after biochar application to soil, previous literature shows that about 60 to 80% of carbon will stay stable there across 100 years. So we used exponential decay model to estimate the carbon losses and emission after we apply biochar, and we're using those decay rate collected from many literature. So this is an example. I want to show you how we model the biochar utilization pathway, and we did similar simulations and modeling for each pathway I showed you previously. So we can have a process level understanding of life cycle environmental impact when we process 1 overdry metric ton of 3 types of urban tree waste. We included 2 linear pathways like landfilling and incineration. And we also include 3 circular pathways like composting, converting merchandisable logs into lumbers and chips for durable wood product, and also converting residues to biochar. The figure I show you here is for the life cycle carbon footprint. different color here shows you the GHG emissions or CO2 sequestration associated with different life cycle stages. For each pathway, you will notice there's a bar in the middle, right? This bar represents the net life cycle result for the total colored bars sum up together. And on the top of each bar, we have arrow bar here. This is because we run the Monte Carlo simulations to consider all the uncertainties. So that's why our results are ranges rather than single deterministic values. So looking at our result, which shows that if we look at leaf waste, doing composting will be much better than doing landfilling. And for merchandisable logs, converting them into lumbers and chips for doable product would be better than other options. For forest residues, converting them into the biochar would be the best options. And a lot of negative value here are associated with the stable carbon stored in biochar. So now at the process level, we identified the best strategy. We also have a very good understanding about how variations of biomass composition changes would affect the life cycle environmental footprint. So we can scale this knowledge up to develop regionalized life cycle assessment and combined with geospatial analysis to understand the potential environmental benefit if we implement them at different locations nationwide. So those are the 6 maps to show the result. The 3 yellow color map is to show you the benefit of implementing those strategies in reducing global warming potential, GWP, which is an indicator to quantify the climate change impact of different greenhouse gas emissions. And the 3 blue color map on the bottom is to show you the benefit in reducing the eutrophication effect. The first 2 map here is about doing composting for leaf waste. The second maps on the middle is to do the merchandisable logs converted to doable wood product. The last 2 map here is about converting residues to biochar. The darker the color, the more environmental benefit this utilization would bring us. So I want to look at these 6 maps together. I just want to highlight 2 major observations. The first one is, if we look at the same type of urban tree waste, like say leaf waste, you will see that the environmental benefits are different at different locations, even though we just implement the same strategy to do composting for leaf waste. Of course, this is related to different biomass availability at different locations, but this is also related to the variations of the composition collected from different locations. Another observation is, if we look at the same region, let me use Texas here as an example. If we look at Texas, we're utilizing leaf waste, merchandisable logs, and the residues to biochar for the same region. Their environmental benefits are different. You can tell by different darkness of the colors, right? So this is really highlights the need of develop region-specific strategies if we want to maximize those environmental benefits of utilizing different kind of urban tree waste. So those doable wood products and biochar, they all belong to nature-based solutions. And in my research group, we have many other ongoing projects related to scalable, nature-based, and engineering solutions to climate change. Like mass timber, I will talk about in the next example. Biochar, already talked about it twice. Advanced wood materials like bio-based plastic, structured materials, biofuels that we can use in vehicles or aircraft. We also have projects related to carbon capture and storage and enhanced rock weathering. And all those projects ongoing in my research group are also related to circular bioeconomy pathways because we mainly focus on utilizing waste woody biomass or waste mineral materials. So looking at the landscape of those projects ongoing in my group, there are 2 questions I find very interesting in recent years. The first one is, what is the GHG mitigation efficacy if we combine some of those solutions or pathways? Because many of those pathways are all related to forest or all related to agricultural systems. So there are a lot of opportunity there to explore possible synergy. Another question is, what are those spatial and temporal factors for those synergetic solutions? I think the answers to both questions are really important for us to identify the best strategies to do synergies. So now I would just want to show you a fresh example. I call it fresh because it's just published this year, where we explored those solutions all related to forest. So this is a project that we collaborated with Professor Mark Ashton, a professor in our forest school, and the first two authors of our paper are my wonderful postdoc, Bing-Chuan and Kai. And in this project, we explored opportunities to restore forest cover on marginal land in the southeast United States. So here are the colored areas are our study region. And we include three types of marginal land: cropland and pasture land with challenging soils. So if farmers want to grow crops on those land, highly likely they want to get a very good yield. We also include forest patches that used to have forest cover, but now they don't have forest cover anymore due to many historical reasons. So if we want to restore forest on those land, there are several ways to do that. The first one is we just plant trees, let them grow. So we call them protection forest. We can also do production forest, or say commercial forest. So we plant trees, we also do harvesting to produce lumber for traditional wood product. After harvesting, we do replantation. And for those residues generated during logging, thinning, harvesting activities, we leave them on site as current practice. They would generate the GHG emissions due to natural decomposition, but they also provide a carbon input to soil. In addition to these two scenarios, we can also design circular scenarios by leveraging some innovative wood product, such as cross-laminated timber, which is an emerging wood product which get a lot of attention and interest from industry because they provide very good material properties and can replace traditional carbon-intensive building materials like concrete and steel. For those residues generated, we can collect them, convert them to biochar, and again, apply them to soil. But we do have a potential carbon trade-off here. When we remove forest residues from forest, we avoid carbon emissions from natural decomposition, but we also reduce carbon input to soil on forest site. While at the same time, we apply biochar to agricultural land or gardens, which can improve soil carbon sequestration there. So what is the system level effect of this potential carbon trade-off? To understand that, we designed two conceptual circular scenarios, which include cross-laminated timber, but also two ideal removal rate of forest residues. So now we have three systems that are highly dynamic and interact with each other. The first one is the forest system that includes the soil. The second one is the manufacturing system that need to produce biochar, cross-laminated timber, traditional wood product. The third system actually include our society and related to the use of product and their end of life. For example, the use of cross-laminated timber in buildings and their end of life. The use of biochar in agricultural sectors and their end of life. So now I want to give you a simplified example to show you how we used the life cycle system modeling framework I showed you previously to model those individual systems, link them together, and generate insight. So this is a simplified dynamic carbon flows across 100 years and also across the life cycle of lumber. Our first step is always develop those mechanistic process simulation models for manufacturing activities and end of life of this product. So those lines here shows you how much emissions, which are positive value, are coming out from our manufacturing activities and also end of life of lumber across 100 years. We then use row C, which is the soil carbon turnover model, to estimate the emissions coming from soil. And we also use the loblolly pine growth and yield simulation to estimate the CO2 sequestration during tree growth. Our rotation cycle is 25 years. So at year 25, we do harvesting, but we also do replantation. So that's why you look at this green line for the lumber cases, you will see a continually growing CO2 sequestration because of this replantation every 25 years. But if you look at the baseline protection forest, which is the two dashed line here, you will see that they almost reach a plateau after certain years, especially towards the end of the years. That is because the growth rate of trees gets greatly slowed down once they become mature. So now we model the individual systems. We also build soft links among each models of them based on the mass balance practice. And we have a good understanding of dynamic carbon emissions and sequestration. We can sum them up together to understand net GHG balances across the entire systems for different scenarios. This is just one result for our low plantation cases. We explore different plantation density and forest scenarios in our paper. But for simplicity, I will just show you one result here. The green bar here is for the baseline protection forest. The number is negative because we have a net removal of CO2 from atmosphere. I put a note here. This is a hypothetical baseline without considering natural disturbance. If we do consider natural disturbance in our future research, I think the number will be smaller than the number shown here because a lot of carbon stored in standing forest may be lost during natural disasters. And here is our result for lumber for traditional wood product, but without utilizing any of those waste woody biomass. So you can see that we can mitigate a little bit more GHG emissions, but not much. And if we look at the result of innovative wood product and biochar, which shows that we can mitigate much more GHG emissions, part of mitigation are attributed to this substitution effect, which are the gray color box here, related to using cross-laminated timber to replace traditional carbon-intensive building material. Another part of mitigation are related to the stable carbon stored in biochar. Those are the results for 100 years. Decision makers may be more interested in seeing short-term results. So we run our models for different years. Here, I will just show the result for 50 years, which interestingly shows opposite conclusions. Our result shows that in a near term, like 50 years, it is likely our baseline protection forest will mitigate slightly more GHG emissions than those wood product cases. So looking at these two opposite conclusions at different time frames, people may be arguing, well, there are a lot of uncertainties and variations in your forest manufacturing systems and in our society, which is true. So we run uncertainty analysis, and this is our result, showing as the red color arrow bar here. Looking at this, you will see that there are a lot of overlaps between our protection baseline and our wood product scenarios, which means how much GHG emissions can be mitigated by our protection baseline can also be mitigated by our wood product scenarios. And we are interested in identify those conditions that can maximize the GHG mitigation of our innovative wood product and biochar cases, which interestingly, again, we find all those conditions are related to environmental and economic factors, like the climate conditions, the forest carbon yield, or the substitution rate. So here is an interesting conclusion I want to draw your attention here. Although these new technologies are an enabler for us to design those circular scenarios, but their overall system-level environmental benefit are actually largely driven by those environmental and economic factors. So those are the results for the entire study region. We also plot the spatial temporal changes maps for the carbon stock of those innovative wood product cases. When I say carbon stock, I mean the carbon stored in standing forest and soil, plus the carbon stored in wood product when they are in use, plus the carbon stored in biochar and all the biomass that have not been fully decomposed in this year altogether. So from year 25 to year 100, you can see that there are more and more regions turn their color from yellow and red color into this blue and purple color, right? So that means there are more and more regions that have a very substantial carbon stock increase, which is great because we want more carbon stored in our system rather than being released to the atmosphere. However, this substantial carbon stock increase in this blue and purple color has a very uneven spatial distribution that I'm sure you can tell by looking at those mixed color maps, right? So again, this highlights the need of develop region-specific strategies if we want to maximize the carbon storage. So far, I have showed you 3 case studies that I hope already convinced you on the importance of using multi-scale system analysis for those scalable solutions. We need those micro level understanding of individual pathways because they are foundational knowledge for us to further understand the impact across the supply chains and across the product life cycle. We also need a macro level understandings, as I just showed you in the previous case study, because they can tell us what are the potential environmental impact if we scale up those solutions or combine them at different locations and across different time frames. So sometimes people ask me, at what level or say at what scale we should pursue such modeling practice in order to effectively support decision-making? My answer is a typical industry ecology answer. It depends. So for engineers who really need guidance on their systems, I think those micro level modeling practice are real helpful. This is a paper we published 2 years ago and received huge attention after publication from academia, but mostly from industry and government agencies. So my collaborators, who are all material scientists and engineers, they develop a new technology to convert this waste wood chips into a black color bio-based plastic film. So I developed several LCA models for this technology. The figure I put here is one of the many results that can show you 10 potential environmental implications of this bio-based plastic compared to 3 commercially available plastics in the market. More importantly, I combined this LCA result with technical performance indicator like mechanical strength and stiffness. So our result helped the entire team to identify the process and material design strategies that can not only achieve desirable material property, but also achieve the lowest environmental burdens. Not only about the environmental impact, sometimes engineers also care about economic feasibility, especially worry about potential trade-offs between economic and environmental benefit. This is from an ongoing project where our collaborators are fabricating and using a nanomaterial made from cellulose, a very important part of wood. And they have a different fabrication and process design strategies. We developed the LCA and techno-economic analysis model to generate this figure to show them where each strategy lay out in terms of production cost, which is y-axis, versus the carbon footprint, which is the x-axis here. We also calculate the environmental cost efficiency, which is an indicator estimated as the differences in the environmental burdens divided by the differences in investment. So this indicator can help us to identify those co-benefit strategies, meaning they can reduce both cost and carbon footprint, or trade-off strategies, meaning people have to invest with more money if they want to use this strategy to reduce the carbon footprint. And we use this indicator to show the extent of a trade-off and a co-benefit. Now we are working on integrating all those tools and indicator all together to a new modeling framework that we hope to offer to material scientists and engineers to guide them how to develop sustainable nanomaterials from biomass. So this is for engineers, for engineering design. For those decisions related to supply chain and management, I want to argue that meso level modeling practice are really important, especially to consider those supply chain networks. And many times, those kind of model may need to be built upon micro level model. So this is from a project we just published this month, which we are so excited about that. So we collaborated with Professor Nova Planavoski, who's a geochemist here, and we studied enhanced rock weathering, a nature-based solution, and we used the waste minerals from a copper mine and applied them to Midwest region in the United States. We used LCA, we used the techno-economic analysis, but for different supply chain design scenarios. And we include all kinds of activities along the supply chain, from the waste sourcing to different transportation ways, and the final application to the agricultural land. So this map is one of our results that include many little maps. The purpose is to show you how the design of a different transportation route, which are shown as those red color arrows here, and also different expectation of carbon capture cost, which is the number I put on the top of each map, and also the different CDR yield, which I put on the caption, how those different variables all together would determine the area of agricultural land that we can actually apply these waste minerals. which I show as this green color circle here. And you can see that the circle size are really different when we have different assumptions. So those results really highlight the need of considering real-world infrastructure and supply chain design when we're trying to scale up any nature-based solution in a way that we hope to be economically feasible, but also meet our expectations of climate change mitigation. For those decisions related to policy and industry-wide initiatives, I want to argue that macro-level modeling will be needed because many times those decisions may cause economy-wide changes, which are oftentimes not well understood and captured by industry ecology methods. So that's why I think developing collaborations with economists are essential in addressing this challenge. So this is a project I work with Professor Robert Mendelson, who is an economist here in YSE. We find our shared interest in wood, wrote several proposals together, and luckily we get funded by YCNCC and Yale Planetary Solution. Really appreciate this funding for this highly interdisciplinary work. Here, we want to understand the global carbon consequences if we will use many innovative wood products in the future. So we develop a regionalized LCA to understand what are GHG emissions and CO2 sequestrations if we fabricate those mass timber products in different regions globally? And our economic collaborators use their models to understand how a new wood demand introduced by those new technology would affect global timber market and therefore affect the global forest land and carbon. We combine these two together in a consistent way to understand what would be the net carbon consequences if we adopt those new technologies in the future under different social economic conditions compared to a business as usual baseline where we just keep doing what we are doing now. This is one of our preliminary results for optimistic scenario that we assume a very high wood demand and also fast adoption of those new technologies. Our result shows that by 2100, we can achieve around like 40 gigaton level of GHG mitigations by adopting those new mass timber product. A lot of those mitigations comes from the increased carbon storage in standing forest and in wood product. Other part of mitigations comes from substitution effect. We're using those products to replace more carbon intensive materials. Many of those projects I have talked to you so far are all related to new initiatives I have developed since I joined YSE 3 years ago, which to me still like just happened yesterday. Time flies, but they are all aligned with my bigger vision in improving industry ecology method, especially life cycle system modeling to effectively support decision-making. So this is from a paper I just finished with several colleagues here, Professor Tom Gradle, Professor Nasima Rao, and also my wonderful postdoc, Kailan. So here we examine different techniques people have used to support decision-making for different decarbonization technologies in industries. And I picked the chemical industry, not because I'm a chemical engineer by training, but because chemical industry is one of the most complicated and diverse industry in terms of their product and technology variety. But it is also the foundational industry because their products are widely used by society and different industry sectors. This figure is to give you a high-level overview of all those techniques we identified. People have used them to support all kinds of decisions from very micro level, like say lab scale decision on what chemical recipe they need to use, all the way to the macro level, like giving suggestion to climate policy or industry-wide initiatives. And if you look at those techniques, you will find that they fall into different disciplines, like material flow analysis, life cycle assessment, they belong to industry ecology. Integrated assessment model, they rely on economics and many other different natural sciences. And engineers have used different techniques to support decisions based on what they need. And in recent years, there are increasing interest in pursuing this multi-scale modeling practice to better understand the cascade effect if we scale up any of those decarbonization pathways that people are developing. So I think if we really want to leverage those multi-scale modeling to support effective and also consistent decision-making across all scale, We need to develop strong and close collaborations among engineers, industry ecologists, and also economists. We also need to develop a tailored modeling strategy to ensure we have a balance between the usefulness of the result and the level of all the technical detail and data we need to run those models. So that's pretty much the end of my presentation. Just want to highlight several takeaway messages. I showed you several life cycle system modeling framework we have developed that can help us understand the sustainability implications of those scalable pathways. I showed you several case studies to demonstrate scale matters. We need a holistic understanding of both natural and industrial systems across space and time. We also need interdisciplinary multi-scale modeling tools to support different kinds of decision-making. And I believe any engineering solutions or new technologies that use biomass needed to be developed hand in hand with proper consideration and management of ecosystems. At the end, I just want to thank our sponsors and also my collaborators, especially my colleagues here at Yale and YSE. This is not a comprehensive list because I know I have many pending proposals with some of you here, which I hope they can all get funded and we have more fun projects to play with. Also, thanks to my external collaborators from institutions in the US, internationally. And finally, I want to give big thanks to everyone, my postdoc and my student in my group, because without them, many of the work I have showed you today would have never happened. Thank you. I'm happy to take any questions.
Thank you, Yuan. Great stuff as always. So you talked a lot about spatial scale. You didn't talk a whole lot about temporal scale. And I was thinking a little bit about how do you deal with some of the temporal scale challenges? Because in one sense, you could make sort of the arbitrary argument that it's all circular economy if we let it run long enough, but that's not particularly helpful. So how do you actually think about temporal scales?
Yeah, this is a great question. I have a lot of temporal scale example, and I have a battle when I prepare this presentation, whether I want to give more temporal scale stuff, and that's may confuse people. So I leave them out. But for temporal scale, I think you are right. There are so many factors and variables that's about the future that can change. So what we usually do is we run those scenario analysis. For different scenario, we try to test how those possible variations of those important factors in the future that may affect our results. Using the our PNNS paper that's forced as example. If you look at the future 100 years, some people may be arguing the most changes people may see is the temperature changes because of the climate change, right? However, if we want to model that kind of scenario in the actual modeling work, which can be really challenging because we need a very good knowledge to about if that changes how the tree grows will be different at different location. So we actually didn't run that kind of route. Instead, we try to understand, well, in the future, we have a good model to understand first, like for those costs of about the different kind of wood product, how they may change in the future. For those potential substitution rates between the concrete, steel, and the COT, how they would change in the future if we assume different optimistic, pessimistic, or middle adoption scenarios. So I would say we try to gauge different kind of scenarios based on our current knowledge about what would happen or what could happen in the future, and try to understand how those dynamic factors in the future along the temporal scale may affect our overall result. Some of them maybe not matter a lot.
We have a couple questions from Zoom. Professor Mark Ashton asks, the state level variations of eutrophication and emissions from waste, would it be better to conduct an analysis at the country level given the nature and distribution of where waste is regarding urban areas?
That's you mean county level or country level?
Sorry, county.
county
Yes,
level.
count.
Yeah, I didn't put our result actually at the city level. Yes, so we actually have a final resolution result. I just didn't show up there because this only have limited time. But Mark, if you're interested, I can share you our result at the city level. We didn't aggregate it to county because we aggregated result based on the urban area, which may include which sometimes overlap with some county boundaries. But we do have the result on the final resolution other than just the state level.
And then Professor Wargo asks, first he says, thanks for the fascinating talk. He has two questions. Does the pyrolysis of biomass release hazardous air pollutants? Wood smoke, for example, contains many hazardous gases and particles, is question one.
Yes, they could. Depends on the technology and depends on how you plant around. Like they may generate some particulate matters that could have human health impact. So for our systems we modeled, we do include some purification at the end, but in the real world, there may be some low-tech pyrolysis that do generate those harmful pollutants that are not well controlled. So that is the issue, depending on those technology around. So I think that is why really we need to do this life cycle assessment for different systems, rather than just current practice, people more towards doing those generic life cycle assessment or average life cycle assessment, just using one representative industrial systems for all kind of pyrolysis. There are a lot of variations and differences.
Thanks, Yuan, for a fascinating talk. I'm glad that you show whenever you do a final assessment, you show the error bars. You know, the error bar is really a combination of using one-car simulation, combination of understanding or lack of understanding at process level, right? And I wonder if there's a way of checking your final mean value. Is there any independent way of checking? Of course, you run a model, the model will output something. How do you know with confidence or lack of confidence the final outcome of that mean value, not only the spread, but also the mean value?
That's a good question. That depends on what system we are checking. So for example, for this arrow bars we showed on those urban tree waste, right? We run multi-column simulation and a lot of input variables are the compositions of those biomass. Those data are pretty solid because they are measured by people, right? So our output are those energy and material flows and environmental emissions estimated by our process simulation model. Those are first principle models based on our understanding of the chemistry and the physical phenomenon. And we can check their energy and mass balance flows by compare them with people who do measurement on their process, like say pyrolysis to produce biochar. The only one that may have large uncertainty on those data is for doing some activity like composting. That's many times happen in the natural environment, have a lot of uncertainties. And for those data, I would say, what we do is we try to collect as many data as possible in the literature, but it's very hard to really verify how each data or the mean value would actually be 100% accurate. Because we all know those environmental emissions are driven by many different environmental factors. There's some understanding about how those emissions may be driven by specific environmental factors like temperature or the soil conditions. And many times we can verify those models by checking some experimental data specifically tested for those models. But if you look at the really large data set, sometimes that could be a challenge.
Hi, Yuan. Great talk. Thank you. I was wondering if you could just say a little bit more about your use of machine learning and your sort of general methodological approach. And the reason I'm asking is because I think of that technique usually as being really good at sort of like describing things, but yet it seemed like you were creating kind of like a causal link in terms of changing things. And I was wondering if does that raise any issues or just a little more about how you're using machine learning in that context?
Yeah, that's a very good question. So I can explain further on how that works. So we actually have a very good process simulation model and chemistry pyrolysis model for that pyrolysis process and activation process. However, the major input of that model is it's better we have not only the composition data, but also know the final yield of the product, like how much biochar you can get out if we just pyrolysis this 1 kilogram of the biomass. These yield data are usually measured by the people who do experiment. And once they get this data,
they directly input into these chemistry kinetic models and the process simulation models. However, if we want to understand what are the impact if I run more than 200 biomass samples, it's just too expensive to ask experimental people to do this 200 times or even more. So what we did is we collected those data measured by people who do experiment. They have limited numbers of data sizes, but we use machine learning to train a model that can tell us what the potential yield would be if my biomass composition would be look like that. And we use their result generated to then feed it into our process simulation model. That's our first principle model based on our knowledge. So I would say the way we use machine learning is not 100% data driven. We are using a hybrid. We are still building knowledge-based model, but we are trying to use machine learning to train some data to fill the data gap that's maybe too time consuming or expensive to obtain by using the traditional approach.
Okay, so for the second question, could the active carbon scavenge pesticides, metals, etc., from agricultural lands? If yes, could the biochar release the contaminants in the future?
This is an emerging area. There are a lot of research ongoing in this field. I'm actually very excited to see those people who do the field work, because without the field work and data, there's no way we model how the effect of those activated carbon and biochar would be if we apply them to soil for those benefits other than the carbon storage. Actually, my PhD student, Hannah here, she's working on this, and she just published a review paper where we briefly mentioned about those potential application area. I keep a lot of faith in those biochar and activated carbon, but how effective they would be, I think they really rely on soil scientists and those people who do field work to test those material and see how they function well in the real field.
Okay, thank you so much. We really appreciate it.
Thank you.